The Linux preamp RPi was a very special patch that was just recently merged into the mainline kernel. With it came a powerful capability, namely the real-time computing. Real-time computing is the ability of a computer system to deterministically process information or react to inputs within a specific deadline. But what kind of systems would require that? Let's imagine, for example, that you're driving your autonomous car. Not driving, you're sitting in the autonomous car because he's doing the driving. Now let's imagine you're driving in a straight line, 60 kilometers per second. Everything is fine, beautiful, perfect conditions, very good. Then you spot a car in front of you. He's driving slightly slower, so eventually you reach it, but everything is fine, there's nothing to worry about. But suddenly this car brakes. Out of nowhere, it just brakes. At that moment, there's a decision to be made. You must also brake. And that decision must be taken very quickly. And that decision is probably taken based on the input of dozens of sensors. And still, regardless of how much information you are given to this computer system, it has to react very fast. How would you guarantee that a computer system would do such a thing? Real-time computing. Now let me give another example. Let's imagine you're now supposed to implement the control systems of a drone that has 4 or 6 or even 8 motors. Those motors, let me tell you, they spin up very fast. Some drones support up to 45,000 RPMs, rotations per minute. If you want to control the drone that has such kind of motors that spin up with that kind of speed, you must have a system, a computing system that is supposed to measure the speed and precisely control the flow of energy into the motors such that you do have a control of the drone, that you can command it to go up or down or forward or backwards. And for that, you need a real-time computing system. Back to the Linux kernel. Starting from version 6.12, the kernel offers users the option to turn on what is known as the preamp RT. And to summarize what this preamp RT is about, it is basically a new kind of scheduler that allows users to run applications in the user space that has so much priority that they are given a lot of importance and are executed without much latency. And thankfully, our friends Raspberry Pi 5 already has a kernel that has this patched included. It is already merged in the new versions of the operating system that ships with the Raspberry Pi 5. Now, although this is an extremely useful feature that will increase the spectrum of applications in the Linux operating system, let me tell you something very important. What it enables is a soft, real-time computing. What do I mean by that? It means that the latency is drastically reduced, but not removed. The Linux operating system will still need computation time dedicated for other stuff in the operating system itself. It will not guarantee a hard real-time capability. Nonetheless, the predictability of the operating system is immensely improved. Another very important disclaimer is that enabling real-time computation will not necessarily increase the performance of applications that are mostly CPU bound. What's that, you ask? CPU-bound are tasks that are mostly limited by the specification of your CPU. This means that the CPU is the main limiting factor of performance, as opposed to I/O-bound tasks, which typically involve transfer of data between different machines or between the machine and a device. Examples of CPU-bound tasks are numerical computation, running algorithms, processing data, running an AI model, so basically things that involve computation or operations, algebra, numbers. This is usually CPU-bound tasks, and again, those will not typically get a boost of improvement if you're going with real-time processing. Are you ready to learn now how to apply the preamp RT in your Linux machine? Let's get practical. In today's experiment, I'm going to show you how to enable the preamp RT in your Raspberry Pi 5. I also dare say that it may work for any other Raspberry Pi that has a Linux version that is higher than 6.12, which comes with the option. Not only that, but I'm going to show you how to even test that. How do you check if your machine has good real-time benchmark? You're going to learn that today as well. And finally, we're gonna learn how to use Docker to benefit from a host that has real-time capabilities, which is quite straightforward, but I'm gonna show you anyway. The main reason I selected a Raspberry Pi 5 to run this experiment is because it is a single board computer, and single board computers are usually the target for such kind of systems. Most of the time, you need a device like this that is connected to something that has to process sensors or process data fast enough to react and have all these real-time capabilities enabled. But nonetheless, if you still want to apply the preamp RT to your machine or your desktop Linux machine or your laptop Linux machine or a different single board computer or the NVIDIA Jetson Nano, it doesn't matter. The steps that you're gonna see today are likely to be the same steps that would work on those other machines, mainly because it is a fundamental process of pulling the kernel, enabling an option, and then recompiling that kernel and rebooting your system. It's pretty much that. That's the start. Before I log into the Raspberry Pi 5, which is already powered up, let me briefly explain the setup. All I did was to flash an SD card with the Raspberry Pi 5 OS lit operating system, which is very easily done with the Raspberry Pi Imager, as you see here at the top left. Select your machine, select the operating system, select SD card, and then you select Raspberry Pi OS Lite. Then you just set up your credentials, whatever user you want, what will be the SSID of your Wi-Fi, if you want to use a public key to authenticate when you log into it. All I did was following the Raspberry Pi Imager steps and also in the documentation Raspberry Pi 5 so far. That's all I did, and currently I can already log into the Raspberry Pi 5. Once you followed all the setup steps, your Raspberry Pi upon boot will connect to the Wi-Fi. And then you have to find out which IP it gets. You can use tools like Nmap from Linux or the Wi-Fi scanner from your phone. Whatever method you use, try to find out what the IP it gets. In my case, it's this one. And then I just type the password of my key and then I'm logged in the Raspberry Pi 5. Now, the very first thing to do is to actually just check if you even have the preamp RT. How do we do that? It's very simple. You use this command, you name dash, and then you're gonna scan through the print line, and here you're gonna see preempt. This means that there's no real-time capabilities in this operating system. Now, a very important remark here is that although kernels newer than 6.12 do have the preamp RT in its source code, it is merged into the mainline. It is enabled by default in your operating system. So what we're going to do today is exactly to learn how to enable that in those newer kernel versions. Okay, so our Raspberry Pi does not have real-time capabilities. Before we follow the steps to enable that, I wanted to show you first how to test. How do you test the performance or benchmark your real-time capabilities of your operating system? Thankfully, there's a patch or there's a package that has that purpose. So that package, let me just do this. Let me grab all the packages in the apt-get. This is the package that we want. Install RT tests. This package has an application that checks and verifies the latency, or how much it takes before your operating system reschedules the same process. Let me give you an illustration to the concept of latency. Imagine you have an application like here, which has to do something every 50 milliseconds, for example, which is a common case if you're processing sensory information like inertial sensors or camera. So your camera has 60 frames per second, or your inertial sensor has an output of 200 Hertz. You want to read that information, do something with it, and then you want to instruct your operating system to sleep until this information is available sometime in the future. That is a very common case. When you tell the operating system to sleep like this happens once you're done processing the information, and then you calculate, hey, I have to do something every 50 milliseconds, therefore I sleep the remaining time, but I want to wake up exactly at the next 50 millisecond mark. And here's the problem. If you do not have real-time computing, there is nothing guaranteeing that you will wake up at the time mark of 50 milliseconds. There's nothing ensuring that, because the operating system can prioritize whatever it wants to prioritize it can switch the context, it can do anything. And if it sees, oh, I have to do this application, I have to allocate time for this application, it might be too late. And therein lies the concept of latency. Latency is you have a 50 milliseconds deadline, but in reality, you woke up at 55 milliseconds. So you had a 5 milliseconds latency. This is what the Linux preamp RT tries to minimize. All right, let's try to test our Raspberry Pi latency. So once you install the package, all you have to do is sudo cyclic test. This is already doing the test. You can set other options that we're going to look into later on. But what's important to understand here is that this test is effectively, in summary, it's a program, it is asking itself to sleep, and it is calculating, some other thread is calculating how much time it takes when the operating system switches back to the program that asked to sleep, basically. And here we see how many times are we running. So this is an interval in microseconds. So every 1,000 microseconds or every 1 millisecond, we are asking to sleep, and then we are waking up, and then we are calculating how much time it takes. And this time is in microseconds. I want to point out that the metrics here are not bad at all. So they are reasonable. So here we see an average of 53 microseconds latency. Sometimes it gets to 141, sometimes it gets to 6. So there is a big range. There is nothing guaranteeing anything. That's what I want to say. And another thing I want to point out is that this is really good weather for the Raspberry Pi. I'm using the lit OS, so the OS is not busy with pretty much anything. It is almost entirely dedicated to whatever we want, and this definitely helps with those numbers. So the lower we see here, the better, and we're seeing reasonably good numbers. For 53 microseconds latency is not too bad. It of course depends on how much you need, but that is not a good use case. Maybe the system, it is stressed with many different threads doing many other things. Imagine I have a system where I have a Raspberry Pi dedicated to measure a sensor, but let's imagine this same Raspberry Pi is also a server that is serving the data via an IoT gateway to some dashboard somewhere. So two threads, and they might collide, so to speak, and that might hinder the performance of this. So again, there's nothing guaranteeing that some other thread might hijack the CPU resource to do whatever it needs to do, and only then we can use this resource back to process sensory data. And most of the cases, we do want priority. Let me now simulate load. Let me simulate CPU load. For that, there is another package, sudo apt update. And while I do this installation, notice that stuff will happen because I will be using the CPU. So keep an eye on this benchmark. So I'm going to install sched.h. This is an application that This is an application that effectively stresses your CPU if you want to. So I'm using the app RPi. All right, I installed a stressor. I'll just start the test over again. It's already have a big number here, but I'll start the stress now. So stress ng CPU 4. Immediately when I used it, we saw a spike in the execution time. So somewhere among those wake ups, we had a latency of 3 milliseconds. That's huge. That can be compromising for some systems, all right? While the system is stressed, I'm gonna do the same test again. I'm stressing. Once more, I had a spike. I'll leave the stress up, and then I'll do the cyclic test again. In many cases, we will hit a spot in time where the CPU simply cannot get back to the thread, to the main thread in time, into the main process in time, because it will be stressed somewhere else. We can also stress the I/O. This will even consume even more CPU time. Again, there's nothing guaranteed. Once more, we hit the latency of almost 4 milliseconds. Again, for some reasons, that is bad enough. What if we had an operating system that would allow us not to worry about that? That is what the preamp RT is about. Just for a complete test, you can also do the test for multiple threads. So here's the same test for the 4 CPUs. Imagine all the 4 CPUs are needed to do something in real time. Yeah, we're gonna have a hard time here because those are not good enough. But they have spikes, and we don't like spikes. One last thing I wanted to point out that while recording this video, I just discovered is that even though we don't have real-time capabilities in this operating system, we can still set thread policy to behave as real-time, and like here, FIFO, and that brings a reasonable increase in the performance of latency. So again, we don't have real-time capabilities yet. I have not enabled it, but I just discovered that even if we don't do it, we get good numbers here, okay? So if we have an application, a C++ application or whatever application, we don't have a real-time operating system, and you want a quick scheduler, even the standard operating system might be good enough for you. But let's follow the steps of applying the RT anyway. All right, so we are still logged in the Raspberry Pi 5, and we are now starting the steps to apply, to turn on the real-time scheduler. For that, we need, first step, we need to clone the kernel. Enabling the real-time capabilities typically involve you cloning the kernel and selecting options, and then we compile it. And that's what we're gonna do. So I went to the Raspberry Pi documentation website, look for Linux kernel. Again, you can do the same steps for different operating system, Ubuntu, Debian, whatever. You download its kernel, and then you follow the same steps. Let's do exactly that. So the first thing I have to do is just apt install Git. If I have not installed it, I have not. And then we cloned the kernel. This can take a while. Clear it. Then we clone the kernel. I just skip it. Perfect. We just clone the kernel. And then we follow the steps once more. We install the tools to build the kernel. Yeah. And then you're going to look for, this is specifically for the Raspberry Pi 5, you're going to look for your architecture. So my Raspberry Pi 5 is the 5. So this is the command I'm going to do. I'm going to set this environment variable. I'm going to set it to Linux also, of course. Then I'm going to make the configuration file, so the .config file, for the same chip that my board hosts. So here we can see config. This is a basic configuration for the chip that we have here. So I'm going to close this. Moving on, you can name your kernel. I'm going to do kernel. And here comes the magic. So at this time, you can do something called menu config. You can actually edit the file, but I'm going to show you a visual. Oh, I have to install this. Apt install. This is kind of a render in cursor. The menu config is an interface to navigate to the different configuration options for the kernel build. Oh, this place is too small. Let me increase this for a second. I'll try again. Nice. This is a very nice GUI to navigate to the different config files, configuration options for your kernel build. And this is how I'm gonna go straight to the preamp RT, enable it, and then save the configuration file. And then we're gonna check if it was really applied. So I'm gonna search. This is the dash preamp RT. Here we see it's, then I press 1. See right here, I press this number, press 1. And you see here that is not enabled. So I go to 1, and I press enter, and then I go fully preemptible kernel. This is the real-time one thing. Then I'm gonna save to this file, exit, and then here we see a yes, and then we can exit. We can double check by going to the config. I'm gonna search once more /preamp RT, and here it's gonna set as yes. This means that, this means that if we scroll down after naming the kernel, if we scroll down and build the kernel, we are building a new kernel that has the preamp RT enabled and selected. That's what we're gonna do now. And this is the longest step in the whole process. So grab a coffee. Just restating that what I did with the menu config, you could have also done literally by editing this .config file, adding this line or changing this line and making sure the preamp RT is enabled. But I always like to do it menu config because it's visual, I can save it, I can confirm it. It's harder to make mistakes with menu config. Perfect. Now our kernel is built. Then we follow the next steps. Just a small thing to remark is that Raspberry Pi 5 is a 64-bit CPU, therefore I use the steps. Moving on, then we install the modules. So we've built the kernel, and we've also built the kernel modules, and this step installs the modules into the operating system file system. So here it's literally just copy paste. It's part of the kernel build, nothing too special. Then we scroll further down and we literally just copy paste those commands. So just for the sake of sanity check, is this variable set up? Yes, it is. Then I would just copy to clipboard. What this is doing is it is copying the existing kernel as a backup. Then it is copying the kernel that we just built into the boot file system firmware and naming it to the kernel that is by default selected. We are also copying device tree. This is a low level stuff from Linux, and also documentation. So this is enough for us to install a new kernel. So if you navigate to boot firmware and ls here, this is our backup. This is the original kernel, and this is the new kernel that we just built. And this kernel has the preempt RT scheduler enabled. Just out of curiosity, I wanted to show you that for Raspberry Pis, in the same folder where the kernel lives, there is a config file, unsurprisingly named config.txt, that allows you to set some kernel stuff, kernel parameters or kernel images. So for example, you could use this file, you could open it, and you could add a new line like this image. This is effectively selecting which kernel image you want to load, and this is the default one, so we don't need to do anything. All right, this is what I wanted to show. If we reboot, we should be loading the new kernel that has the preempt RT. So let's do just that. Okay, the Raspberry Pi is back online. Our SSH into it was more. Same credentials, the same, everything is the same. Have a look here at the top, preempt RT. And if we do this as well, we have enabled the Linux real-time operating system, as you can see. So we have preempt RT. This means that we can set the real-time scheduling policy to applications and programs. So if I would do the cyclic test again, which is already installed, of course, as a sudo, we see the same thing. And if I select the policy to FIFO, we should see a better time than we saw before. So it will be difficult to remember, or even difficult to measure for good, but the times that we got before were on the range of 1 to 10, and here we have a lower number. Like I said before, it was a bit of a surprise to see good numbers without the RT, but this is the best that you can get. If you enable the real-time operating system and do cyclic tests and use the scheduling FIFO policy, you're doing the best you can with the operating system. So if I call stress ng CPU 4, IO 4 as well, just for you to see, this is really stressing the CPU. So this is document, we see a bunch of CPU load. If I do the cyclic test, it almost doesn't feel anything. Why? Because the operating system is giving a lot of priority to this task, to the task of cyclic test. So this is, again, this is the best that you can get using the Linux as of now. It's important to see also that you could set priority. So even if you have multiple processes with the same scheduling policy, you could theoretically set different priorities for each. So they could have priorities among themselves. So here is setting the absolute maximum priority for FIFO, which is real-time operating system policy tasks. Another policy that you can use is a round robin. This is also real-time. Not going to discuss the details. FIFO is usually the fastest. So if you want the best latency, you're going to go for FIFO instead of round robin, and you're going to give it the highest priority. Also, out of security, just check available policies right here. So if you go policy, other, this is a typical scheduling algorithm priority, and then you have batch, idle, FIFO, or round robin. And keep in mind that everything that I just showed you with the cyclic test, it was done while the CPU was under stress. So it is a powerful tool. If we set threads to 4, we see very close high latency performance. In the final part of the video, I want to show you how you could set the scheduling policy of your process or your application in case you want to programmatically switch that to make sure this process gets the best scheduling policy and the best priority. One way to do it is via C and C++. There is a header file that allows you to call this function, and this function effectively tells the current process should get the scheduling policy FIFO, which is this real-time good policy, and you can set off the priority to a number like 99. Okay, and this program that I did, it is a program that calculates it solves a non-linear optimization problem, and for the sake of this test for the latency, I added an option that I either switch the policy to real-time or not, and then we can compare. And this part of the video is also to show you how to use this program as a test with Docker. So now we're gonna see how to set up our Docker to call programs in the container that needs a policy of real time. Let's see how that works. So the program that I just showed you, I've pushed it to Docker Hub and I'm gonna pull it like this. So this program that, again, I just showed you, it sets its own scheduling policy in the program itself. And depending on the argument that we give it, we set it to a real time or not. So the first thing we do is just to pull this image, and then we're gonna use Docker commands and Docker parameters to set up our scheduling policy, or at least permission to the container to access the real-time capabilities of our host, which is the Raspberry Pi 5 right here. While we're still pulling the image, I wanted to show you another method to set the priority and the policy of processes that are already running. So there is a Linux command called CRT. It's called for its help. The way it works is you specify a process, you specify the policy, and you specify the priority that you want to give. So as an example, let's just pick any priority, any program here. We can use the Docker. So this process, I can set it to real-time priority, the real-time policy and priority, just by doing the following. So sudo srt policy option. I'm going to use the FIFO, and then I'm going to set the priority to 99, and then I'm going to select the process ID, which is 2019. So to check that, we just do this. I've just selected this process to be FIFO policy, which is real time. If I check another one as an example, 1913, it is schedule order. Let me set it also to FIFO. Then I can check it again. Now it has been assigned as a FIFO and high priority. All right, this is another method in your Linux shell that you can do to set up policies and scheduling priority. Okay, we've downloaded a Docker container that has this application of optimization problem and has also real-time policy thing. This is how you enable your container to use real-time capabilities from the host. We add this option to allow the container to switch and assign priorities and policies. Then we set a limit on the top priority of 99, and that should be it. That should be enough for our application to self-assign the priority and the policy as a real time. What comes next is the Docker container name, the image name, and this is the argument of the program. The first argument is in how many microseconds we want to schedule another optimization problem. So the smallest of this number, the more stressful, and this is enabling or disabling the real-time capabilities. So let's start with it disabled. So every 50 milliseconds we are computing a problem. It is taking sometimes 21 milliseconds, sometimes 33. It's quite reasonable. And I'm also doing the same thing of the cyclic check, where I store the largest number. So far, nothing special. I'm not using real time yet. And so far, I also got a latency of 109 microseconds. If I stress my CPU like this, I do expect a larger latency. And I'm gonna stress the I/O as well. Yeah. Okay. So here we start to notice some problems. So already I got a latency of 3400 microseconds. Sometimes it's 200, sometimes it's 85. If I restart the process with a smaller, so more frequent wake-ups, yeah, sometimes I even get an overrun. This means that I was not fast enough. Sometimes I got give you such a huge latency that it compromised my timeline, my deadline. Okay, so this is too stressful. Let's try 40. Okay, sometime we already got a huge latency because of the stress of the CPU doing something else, which again can be can be hosting a server, serving some requests, and doing measurements on the sensor, computing an optimization problem. Yeah, I can be doing a lot of stuff, and I can be compromised if I don't have any real-time setting. So yeah, again, 34, 130, it's horrible. It's not good. If this is running on a device that is supposed to compute this problem of the optimization problem within a strict timeline, I am screwed. So let me turn on the real-time policy. Look at the difference. So here I'm computing, I can even go stricter, more strict. Now I'm stressed, my CPU is stressed, and I can still guarantee that I'm solving the problem, my computational problem, in about, well, every 30 milliseconds with this very small latency. This is the greatest, well, it's opinionative. This is the greatest example I can give where I have a problem, I'm stressed, but I can still guarantee that I'm gonna solve the problem. I'm gonna make the CPU go back to the process just in time to continue with the second iteration, and that goes on and on. That's it for this video. I hope you have learned something new. I hope this is a good knowledge for you to have when thinking about real-time operating systems, real-time applications that demand strict timing from processing data. I hope that whatever you saw here today is good for you to at least get started with those kind of projects. Thank you very much for watching. Until next time.